In this video, we're going to graph a rational function that has a quadratic in the denominator and none of the linear factors cancel out, so we don't get any holes. So we start by factoring numerator and denominator. We get x plus 3 times x plus 1 over x plus 4 times x minus 1. Now, we see that we've got a couple of factors in the denominator and neither one of them crosses out with anything in the numerator. We're going to have a vertical asymptote at x equals -4, and we're also going to have a vertical asymptote at x equals 1. Now, we see that after simplifying, we still have x's in the denominator, so in order to figure out if we have a horizontal or oblique asymptote, we're going to compare degrees. We've got degree 2 over degree 2, so we can say that we've got a horizontal asymptote at y equals lead coefficient over lead coefficient. Well, both of the lead coefficients are 1, so we end up having a horizontal asymptote at y equals 1 and a couple of vertical asymptotes as shown. No holes. Now let's determine the intercepts. If I let y equal 0, to determine the x-intercepts, I get 0 equaling x plus 3 times x plus 1 over x plus 4 times x minus 1. So I multiply both sides by the denominator on the right. I get 0 equaling x plus 3 times x plus 1. That means x is going to equal either -3 or -1. So I've got a couple of x-intercepts. One's at -3, 0, and one's at -1, 0. Now, how about my y-intercepts? Well, my y-intercepts, I can just plug in an x value of 0 to this factored form, or, if I want, I can go back to the original. I'll get the same result either way. I end up with 3 times 1 over 4 times -1. So I've got a y-intercept at -3/4. So all three of these circled points here will be significant on my final graph. Let's do a vertical asymptote analysis. We, as you might recall, we have a couple of vertical asymptotes here. One's at x equals -4, one's at x equals 1. Starting with x equals -4, we can let x equal -4.01. If we do that, then y is going to equal -4.01 plus 3 times -4.01 plus 1 all over -4.01 plus 4 times -4.01 minus 1. And after doing all of our simplifying, we get an answer of positive 61. So that means that to the left of the vertical asymptote, y is going to be heading to infinity. Now, let's let x equal -3.99. And if we do that, y will be -3.99 plus 3 times -3.99 plus 1. Obviously, on a test, you don't have to show all these steps, but just so you see what I'm doing, figured I'd show them. And what we end up here is a number of approximately -59. So that means that to the right of the vertical asymptote, y is going to be heading to -infinity. All right, now let's take a look at this other vertical asymptote. We can let x equal 0.99. Well, plugging that in, 0.99 plus 3 quantity times 0.99 plus 1 quantity over 0.99 plus 4 quantity times 0.99 minus 1. And we get an answer of approximately -159. So that tells me that to the left of that vertical asymptote, y is going to be heading to -infinity. And if I let x equal 1.01, then we end up ultimately with a value of approximately 162. And so what that tells us is that, let me finish this out here. What that tells us is that to the right of this vertical asymptote, my y value is going to be heading to positive infinity. All of that's pretty useful information. All right. So now let's do a horizontal asymptote analysis. Well, to do that, we can let x equal negative 100 and find out what y equals. Well, if I let x equal negative 100, y is going to be negative 100 plus 3 times negative 100 plus 1 all over negative 100 plus 4 times negative 100 minus 1. That equals 9,603 over 9,696. That's slightly less than 1. Now, why am I comparing it to the number 1? I'm comparing it to the number 1 because that's my horizontal asymptote. So this tells me that as x approaches negative infinity, because negative 100 is pretty far to the left, the curve will be approaching y equals 1, the horizontal asymptote, from below. Okay, so keeping on then, let's go to the far right. If we let x equal 100, then we'll obviously get a different value for y. I guess we could get the same value theoretically, but we won't in this case. We end up with 10,403 over 10,296. And since the numerator is greater than the denominator, we can see that we're above 1. That means that as x approaches infinity, the curve approaches the horizontal asymptote from above. Okay. Okay. Now, moving on. It's a good idea in these sort of cases here, and you'll see why in a moment. It's a good idea in these sort of cases here to determine if the curve crosses the horizontal asymptote. Remember, curves can cross a horizontal asymptote. Now, if the horizontal asymptote is at y equals 0, you've already determined if the curve can cross the horizontal asymptote when you determined if there were any x-intercepts. But in this case, the horizontal asymptote is y equals 1. So what we're going to do is we're going to sub in a y value of 1. We're going to see, does y ever equal 1 in this rational function? So we let y equal 1, literally, and then we multiply both sides by the denominator on the right. Okay, and we get this expression here. Now we can factor it out, or sorry, expand it out. We get x squared plus 3x minus 4 equaling x squared plus 4x minus 3. The x squared terms cancel out, and so we just have 3x minus 4 equals 4x minus 3. Or sorry, this should be a plus 3. My apologies. That's a plus 3 and a plus 3. Now, if I subtract 3 from both sides and I subtract 3x from both sides, I get x equals negative 7. What that tells me is that one of the points on this curve is negative 7, 1. Now, why is that important? It's important because that's the y value of the horizontal asymptote. So what we do then is we put it all together. If we look at our vertical asymptote analysis, we'll see why these arrows are where they are. If we look at our horizontal asymptote analysis, we'll see why these arrows are where they are. If we look at where our intercepts were, we'll see why these points are here and why that point is there. And the very last thing, we see that we actually do cross our horizontal asymptote. Now, what we're going to do is we're going to do our best to draw a curve that meets all of these conditions. So we're going to cross through here. We can't cross the x-axis, though, because we can't cross that x-axis because our only intercepts were already accounted for. But we're going to have a minimum point somewhere, and we're going to come back up, and we're going to treat this as a horizontal asymptote and approach it from below, which our horizontal asymptote analysis told us we should do. Now, you might say, where's that? The answer is, where's that point there, that minimum point? The answer is it'll come to you in calculus when you learn calculus. So then we do our best in the middle here. We try to treat that those vertical asymptotes like vertical asymptotes. You might say, okay, sir, well, where's that maximum point here? We didn't know where the minimum was over here a minute ago. Where's this maximum? And the answer is you'll learn that when you do calculus as well. So there's a little bit to be desired here, but we're just doing our best. And then over on this side, it's a little bit easier. We're just going to draw our best curve. You might say, well, how far down should we go here? And the answer is, if you want to know that, just plug in a point. If you wanted to let x equal 4, you could find out what that y value is there, and you'd have a better idea what that curve looks like. Anyways, that's extremely sloppy, but here is a better version. And as you'll see, what we were saying a minute ago, we don't know exactly where that minimum point is until we learn derivatives. We don't know exactly where that maximum point is until we learn derivatives. And this is the best curve that we can draw, knowing what we know.